Hi all. In the previous video on backpropagation algorithm in artificial neural networks, we learned about the architecture of ANNs in general and how to use that to learn a function between the input and the output. And as we saw, the learning process essentially consists of estimating the weight parameters of the ANN network. And the way we estimate these weight parameters is by using gradient descent, but gradient descent used in its naive form is very computationally expensive, and so we use this backpropagation algorithm, which is essentially implementing gradient descent in a very efficient manner. In particular, in backpropagation, instead of taking a derivative of the cost function with respect to all the weights of the network, we can do it layer by layer, which makes the process very efficient both in terms of computational complexity as well as mathematical formulation. So now there, as you must have noticed, that the way you compute the output from a given input is through computation of the values of the hidden layer nodes, and each hidden layer node is composed of a linear combination of the values of the nodes of the previous layer passed through an activation function. So a choice of this activation function is actually very crucial for this ANN to work. So in this video, we are going to learn about the various kinds of ANN activation functions that one could use for solving a given machine learning problem. Now, of course, our discussion is not going to be exhaustive because in principle there could be an infinite number of activation functions that one could use. But what I am going to introduce you to is a set of the most general or the most common functions which are used, which you can also use for your analysis. And then we are also going to see some optimization methods that are used in artificial neural networks, because gradient descent is fine, backpropagation algorithm is fine, but still there are some issues that you need to take care of in order to make your code further practically efficient. So now artificial neural networks can be used for regression as well as classification, but classification is something what ANNs are used more commonly for, so we are going to focus mostly on classification. So for the sake of simplicity, if we refer to the case of binary classification, then one could say that our activation function could be something like this. So this is sigma, the activation function, and it is a function of the weight parameters as well as the input value. So here x could stand for the input value or the nodes of the hidden layer. Okay, so here I'm not differentiating between the two. So now if we are talking of a problem of binary classification, then a very simple choice for the activation function could be something which is, let's say, 0 before a certain threshold and it is unity after a certain threshold. This would perfectly mimic the idea of a binary classification problem. But a problem with this choice for the activation function is that this has exactly 0 value for the gradient on both sides of the threshold. So, as you know, our ANN weight learning method uses gradients of the cost function, which is a function of the activation functions. So now if your gradients are exactly 0, then there is no learning happening. How on earth are you going to learn what function it is that maps the input to the output? So although this is an intuitively nice choice, but from a implementation perspective, it doesn't help us at all. So where do we go from here? So the simplest modification that you can do to this, which we did for the case of logistic regression, is to use what is called the logit function or the sigmoid. So there, instead of going abruptly from 0 to 1, you do a smooth transition from 0 to 1 through the use of the sigmoid function, or it is also called the logit function, as you must be aware of. So this is a very commonly used activation function for artificial neural networks, and as we saw in the case of logistic regression, a very good thing about sigmoid is that it not only tells you which class your given input lies in, but it also gives you a probability estimate. So for example, if your parameter values correspond to this, then you know that the probability of your given input lying in class 1 or class 0 is exactly 0.5, and as you move to this side the probability slowly increases to 1, and as you move to this side your probability slowly decreases to 0. And of course this has changing gradients. As you move from here the gradients are 0, the gradient slowly increases, then again it starts decreasing till the gradient again reaches 0. So in this portion of your sigmoid function, the gradients are non-zero, and that is what helps you in learning the weight parameters. And this sigmoid was originally a common choice for both the hidden layers as well as the output layer. However, slowly over time, its use for the hidden layers has dropped down. And the reason is that although your sigmoid function has non-zero gradients over here, its gradients in this region and this region are 0, or even if not exactly 0, they are very small. So if your parameter values or the input values are in this range, then again your learning becomes very difficult, because if the gradients are small, your weight parameters are not going to be updated. And because of that, the sigmoid function is now largely used for the output layer, because that is where you need to do a classification between 0 and 1. But for the hidden layers, which are not really meant as the output layers, there you use some other function which doesn't necessarily have to be between 0 and 1. And of course, the sigmoid function is what is used for the case of binary classification. If you have a multi-class classification problem, then instead of the sigmoid, you use the softmax function, which I had introduced you to in the multi-class classification video for logistic regression. So in case you don't remember what the softmax is, take a look at our multi-class classification video. So this problem of the gradients becoming very small is what is referred to the vanishing gradient problem. These artificial neural networks suffer from the problem of vanishing gradients as well as the problem of exploding gradients. Now again, going back to the backpropagation video, you can see that if you have a artificial neural network with lots of hidden layers, then as the information backpropagates from the output layer to the input layer, we have several multiplications taking place. And so if your gradient is, let's say, very close to 0, then if you multiply it with other gradients which are also very small, then they will slowly all decay to 0. And so at the end you are learning nothing. The other extreme is what is called this problem of exploding gradients, which means that if your gradients are very high and if you multiply them repeatedly, then they are going to explode into a value which is again very high and will lead to again problems. So because of the problem of the vanishing gradient, we avoid using the sigmoid activation function for the hidden layers. Now of course the exploding gradient problem does not happen for sigmoid, because your sigmoid's output is restricted to between 0 and 1, but it can happen for some other activation functions. So now in order to take care of the vanishing gradient problem, what was proposed and what is used very commonly for the hidden layers is what is called the Relu activation function. Relu stands for rectified linear unit. So what is this? What does this Relu look like? So again you have your x-axis which contains the weight parameters and the input values. This is the activation function, and your actual function is 0 for left hand side of your x-axis, and for the right side it is a linear function. So this is a perfect straight line with a positive slope. So this leads to a much faster training algorithm because it does not suffer from the problem of vanishing gradients. So your gradients do not decay down to zero, and that is because your function does not saturate to unity. Now, of course, Relu has a problem that on the left hand side it is 0. So the gradients here are always going to be 0. And because of that, sometimes, I would not say always, but at least for some problems, you replace this by a variant which is known as leaky Relu, where the activation function output on the left hand side of the x-axis is not exactly 0 but a negative number which is very very small. So this can take care of the vanishing gradient problem on the left hand side. So as I mentioned, for the hidden layers, Relu is usually the default choice, and for the output layer you use either the sigmoid or the softmax depending on whether you have a binary classification problem or a multi-class classification problem. So now, as I mentioned, that this is not an exhaustive list by any means, because practically speaking you can have infinitely many number of activation functions, but these are the two activation functions which are most commonly used in ANN. So now that we have looked at the various kinds of activation functions, let us look at the various optimization methods that are used in artificial neural networks. What do we mean by optimization? So optimization for ANN basically represents the various ways in which gradient descent is implemented. Now, of course, you do gradient descent using backpropagation, but even there are some further variations that one can use in order to speed up the convergence of our algorithm to the desired solution. So now the idea is that let's take a simple example of the weight parameters, and this is, let's say, the final cost function. And now if your cost function as a function of theta was, let's say, a nice convex function. So here what happens is that in gradient descent you start from this location, you move in the direction of decreasing gradients. So now you move here, you move here, you move here, you move here, and slowly what you do is that you converge to this final point which represents the minima. And now this is fine for the case of logistic regression. But what happens in the case of ANNs is that the loss function is not convex. So your actual loss function could be, let's say, something like this, which is highly undulating, a very complicated kind of a landscape. And so now what happens is that if you implement your simple version of the gradient descent, and let's say you start from here, then you will descend, 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 and get stuck over here. But that is not really the best solution that you want. You would want the cost to be minimized further. So ideally you should either choose this as your minima, or perhaps choose this as your minima. These two are kind of close by, so it doesn't really matter which one you choose to. But this is definitely far away. So because of this, the simple application of gradient descent, even with the use of backpropagation, is not very efficient for the case of artificial neural networks, precisely because of the non-convexity of the cost function. So now what you do is that instead of using gradient descent in its original form, what you do is that you use what is called stochastic gradient descent, or in short form it is also called SGD. So in stochastic gradient descent, what we do is that instead of computing the cost function with respect to all the various input data values, what we do is that we take the cost function with respect to smaller sets of data values. The smaller set could be as small as just one data point, or it could be, let's say, a fraction, let's say 10% of the data points or 20% of the data points. So because of that, what happens is that there is a stochasticity or randomness which is introduced in your gradient descent. So now, instead of doing this simple gradient descent from a point to the nearest local minima, what happens now is more of a random jump. So let's say even if you start from here, your jump could actually be from here to here. You could actually do a stochastic jump till this point, and then again you can do a stochastic jump till this point. And because of that, there is a possibility that you converge to the actual global minimum of your cost function. And this is happening because if you take a smaller data set than the entire data set, then your cost function is no longer this, because this cost function with respect to theta came about because when you took all the data points in your repository. But so now if you take a subset of your input data points, then of course the variation of C will be different, and because of that the gradients will be different, and because of that the jumps will not necessarily follow the direction that comes about when you take the entire data set into account. So now, as I said, when you do this stochastic gradient descent, you could either take one data point at a time, or you could take a subset, a fraction like 10% or maybe 20%. And usually it is a fraction which is taken because, taking a single data point does increase your stochasticity or randomness, but it again makes the algorithm very, very slow. So you want something that converges to the global minima or close to the global minima, but is also fast enough from a practical perspective. And there, your choice of the batch size comes into picture. Now, how large the batch size should be is very hard to say a priori, but some choice based on trial and error has to be arrived at. Now, there are many other variations of stochastic gradient descent which are available in the machine learning community as Python packages. I'm not going to get into all those details, but we'll just introduce you to two other variations of stochastic gradient descent that one could use. Now, as I mentioned that, it is possible that when you take a smaller data set, then instead of following this curve, you may actually jump around. Now, the other thing is also possible that, when you take a smaller subset of your data set to do your gradient descent, you may just move, let's say, a smaller distance from here to, let's say, just here, and that is even smaller than what may happen when you take the entire data set into account. So in order to speed up this process of gradient descent, what you do is that you add a momentum term to your stochastic gradient descent, which means that instead of just taking the gradient, you actually amplify the amount of distance covered through this momentum term. But one problem with adding a momentum is that, if the momentum is very, very large, then what may happen is that instead of jumping from this local minima region to this local minima region, you may jump from here to here, which is again a local minima, but it is again higher than this value. So you do not want the jumps to be too high also. And so you need to make the jumps a little more rational, and you also need to ensure that your jumps slow down before you again randomly move to some other region. Stochasticity and randomness is helpful in exploring a larger set of local minima in your given cost function landscape, but you also do not want to keep exploring forever. Finally you need to settle down. Finally you need to converge to some kind of a minima. Whether it is a local minima or a global minima is impossible to tell, but you at least want to converge to something that is practically meaningful. So because you want to achieve that, you do not want a momentum term that is too large, which helps you in exploration but does not allow you to settle down. So for that, there is a variation that is used, which is called Nesterov SGD. So what is Nesterov SGD? So in Nesterov SGD, what you do is that you estimate the gradient of your future value. So let's say you are currently over here, and using the momentum term, you are going to take a jump over here. You, before taking the jump itself, you estimate the gradients at this point, and then you use that to decide how far you want to jump. So what you do here is that instead of just adding a momentum term to your stochastic gradient descent, you actually estimate the gradients at the future point where you're going to jump to, and use that to modify the extent of your jump. So I'm not getting into the mathematical details because that requires a lot more analysis. But what I would like you to understand is the basic idea and the different variations which are possible. So these are some of the, I would say, the more classical ways of doing gradient descent. Nowadays, there are many other methods called AdaGrad, Adam, and several other adaptive gradient descent methods where you don't just add a momentum term, but even keep changing the learning rate as you explore your cost function landscape. So the point that I'm trying to make over here is that you need to add some amount of stochasticity to your gradient descent in order to first make the algorithm converge faster, and secondly to ensure that the algorithm converges to something that is closer to a global minima. And that is because the ANN cost function landscape is non-convex. So although we cannot be sure that whether we have converged to a global minima or not, but at least we should develop an algorithm that allows us to explore a larger portion of the cost function landscape and not just confine ourselves to a particular local minima. And this is also why initialization of the weight parameters is very, very important, because if you do not initialize them well, you are again going to be stuck in some local minima or not learn anything at all. So there are, nowadays several Python packages available which do all this job for you. So when you use a artificial neural network package using TensorFlow or PyTorch, it gives you all these various options which you can explore. Now, which particular stochastic gradient method and which particular activation function will work best for you, that is something that you need to figure out by trial and error. But generally speaking, your optimization method has to be some variant of the stochastic gradient descent, because the usual standard gradient descent is very, very slow and often converges to a local minima. So I hope this video was useful to you, and in the next video we are going to learn more interesting concepts about artificial neural networks. Till then, stay connected.